Okay, it's coming. Yeah, it's looping. Yeah. Yeah, I think I need to do that right now. Where's my? Where's? Wait. Oh. Wait. But I already mute myself, so oh, okay. I need to mute the speaker. Okay, now it's good. Test, 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 test. Yeah.
Just say hello to you. I'm Lilia.
Oh,
Hi.
yes. Okay. Nice to meet you. So everything is good here?
We don't see.
Yes, I'm sharing right now. I mean, should I join the Zoom again? Yes. Hello. Over distance. Yeah, I'm trying to get the.
What are you sharing?
Yeah.
Just
Can you get the
I think yeah. I think it's shared.
presentation up?
Yep. Okay. Wait, just a bit. Yeah. You see it now? Okay. Now we have a problem.
What's the white screen?
It's just a white screen. And,
What are your problem? What are you trying to do? To get the Zoom meeting start? To get his Zoom meeting?
the screen is not sharing in Zoom.
Yeah. So get the Zoom meeting. So.
Yeah, it should be here.
No,
But I mean, they can also share it, but this is not going to work.
Can you share a presentation instead?
Yeah, I mean, this is
No,
just
that's
the desktop, so I guess that's.
okay. Okay, let me try to. You good?
Yeah. Now you see. So now put it in presentation. Do you want to have Do you have text that you want to see?
Yeah, here.
Yeah. Then I'll show you how to do
I think.
because,
Yeah, I mean.
okay.
It should be fine.
And you see just that. Yeah.
And others. It's good.
Yeah.
Okay. Okay, I will open your presentation first. Yeah. Yeah, I have other here.
Yes.
Okay.
So can you also
But can
just put it up
put it up so that it works.
Okay.
And it works.
Working? In Zoom, I mean. Okay. Okay, I'm leaving.
Do we have more than one of these? Because then I think you can get this one on. And I will actually just use this as a Var sätter jag igång den här? So we'll wait till exactly that watch is, we'll do the time in the room and not the time in real life, because otherwise we'll just get confused.
Sure.
So can you hear me, Hilda? Yeah. So I'm telling everyone who's might be in audience away that we are waiting for the clock to be 9 o'clock here before we start, because we should start formally at the right time.
I do go. Double check the phone.
So resource? Yeah. There instead. No, I just want people to be collected. It's easier if we have the camera and so on. So yeah, you can also. Yes. Because I want you to be close to him.
I was thinking that should be the case.
Yeah. Now the time. Now Fredrik is telling me. Now, so just now. I will do it like this so that people can hear me. So welcome everyone. Welcome everyone in the audience here, and welcome everyone on YouTube to this dissertation where Grant is going to defend his thesis, Reversible Electroporation of Tied Basil Leaves as a Pre-Treatment Prior to Drying. So Grant is, of course, the key person here today, but we also are lucky to have several other people that will participate. So first of all, we are very honored to have Professor Artur Victor from the Department of Food Engineering Process Management of Warsaw University of Life Science. That was too long to say.
Yes.
Professor Victor is a leading expert in the field of drying technologies and the use of pulsed electric fields in food applications. And we are very happy and honored to have you here. We have also a committee who are the ones who decide whether we have a new doctor today. And that is Professor Lily Anne from the Department of Food Science at the University of Copenhagen. Professor Anne has a long tradition in food and food engineering, and her expert field is the effect of process on physical, chemical, and structural characteristics of food. And we are very happy that you are here. And then we have Dr. Gerard Hofland, who is a general manager of the company CO2 Dry in the Netherlands and chief technology officers of the company Phacon in the Netherlands. He holds also a PhD from Delft University of Technology. And I think you are here to represent what is very important for an engineering faculty, and that is the industrial perspective of all of this. Finally, we are grateful for having Professor Leif Bülow from Lund University and the Department of Pure and Applied Biochemistry here. Leif is a director of Scan Oats as well, and has a very wide experience, I would say, when it comes to plant science and the use of plant material and technical applications. Finally, we have two deputy members So if anyone here should decide that for some reason they cannot continue in the committee, we have someone to step in. And first of all, we have senior scientist Birgitta Raholt from RISE in Sweden, and she has a very broad experience also in advanced process techniques. And then Dr. Andreas Håkansson from our Department of Food Technology and Engineering, who's working quite a lot with process engineering. So the process today will be that the opponent will put Grant's work into the bigger picture of science, and then Grant will present his thesis, and then we will have a technical break, and after that the Q&A session will start. So I will leave the word to you, Professor.
Yeah, thank you. Okay. Your committee, dear guests, it's my pleasure and honor to be here. I think that I'm even more honored to be here than you are by my presence here. Today I will share with you some of my experience, and I will try to give you the background of pulse electric field and try to put, let's say, of course, the grant thesis in the area of pulse electric field. So I am the assistant professor at the Department of Food Engineering and Process Management in Warsaw University of Life Sciences in Poland. So if you will have any chance to visit Poland, just let me know, and I can be your guide over there. So before we will move to the merit of this presentation, I would like to move back to 1987 and see what happened that year. So it was a very important year for the world that time. Of course, each year is important. So let's see what happened this year. So great speedway rider Per Johnson won Swedish individual speedway championship. I'm a big speedway fan in Poland. This is very popular sport. In fact, one of our cities, Toruń, we have a street named after him. So he joined the team of Lech Wałęsa. People still that alive and have street named after them. Metallica played the first concert in Poland. I have heard from my mother that my sister went there without her permission. It was a beautiful concert, by the way. That's what I heard. The first episode of The Simpsons and Married with Children aired, and a little known Polish scientist Artur Wiktor has been born, which I hope at least my family found as an important event, let's say. So all of these events were more or less important, but the one that you see here in this slide was the most important, I think. So in this year, in 1987, commission led by Mrs. Brundtland published the report on sustainable development, our common future. So this is the first time when they have decided and did, let's say, the political definition of sustainable development. According to this definition, it was a development that will meet the needs of the present without compromising the ability of future generations. So they have established the development into three pillars, yeah, economical, demographical, and environmental, let's say. And this political definition influenced almost all of our activity domains, areas. It did change the thinking about the food processing as well, because we understood that we need to find new solutions. We need to find methods that will allow us to produce better food with lower environmental impact and lower energy consumption. And pulse electric field, in my opinion, and I will try to, let's say, show you that, is such a solution that truly meets the requirements of this concept, of sustainability concept, and it fulfills that completely. So what is the mechanism of this process? So let us imagine that we will put an apple, let's do it apple, why not, between two electrodes that are charged. So apple, of course, as each biological matter, is built of cells, let's say. So if we will have a closer look and we will try to simplify the situation a bit, we will deal with something like that. In the biological cell, we can distinguish different, of course, structures. For instance, cell membrane, which I know that scientists are here, so I'm sorry for such a simplification. Let's say that it's an envelope that keeps the cell together. In turn, inside the cell, there is an intracellular matter that is made of water and other compounds that are diluted, let's say, in the cytoplasm. Those could be secondary metabolites, substrates, enzymes, and other different compounds. Now imagine that high intensity electric field will be applied to the system between those electrodes. So if something like that happens, so we will have the voltage between the electrodes due to some different factors and different mechanisms involved in the process, this electric field will rupture the continuity of the cell membrane. And it will induce, let's say, its perforation and the mass transfer from inside the cell to out. To outside the cell will be facilitated. So water and other compounds diluted in the cellular juice, they could be transferred easier. And this phenomenon, this process is called electroporation. And this is why are we here, in fact, electroporation, connecting the people. So this electroporation can be defined, let's say, as an electrically induced perforation of the cell membrane. It can be reversible or it can be irreversible, depending on the many parameters which can be related both to process itself or product. This is very good information that this process can be irreversible or reversible for scientists, because we can do a lot of stuff with that. So in some extent, we can say that the sky is the limit. You can see that there's a number of possible applications of PEF in a food and non-food processing, from freezing, juice yielding, drying, to some more sophisticated applications like, for instance, stress reaction implementation. And we will go through some applications in a moment. By many scientists, pulse electric field is still considered as emerging technology. But in fact, if you will have a historically look on it, it goes back to the late 40s of the last century, to the Ukraine, which I think that our all, let's say, thoughts are now, where Boris Flomenbau and Anatoly Zagurulko worked on the technology and patented the technology. So it's pretty old technology, I would say. Yeah. Well, when it comes to food industry, it's a new technology, yeah, because I'm like, what's new in the food technology? Microwave oven, yeah. This is what people sometimes say. Another father of this technology originated from Germany. Heinz Divenspech was one of the first engineers, let's say, that studied the principles and applications of pulse electric field. So you see that it's emerging, but still not so young. And let's move to the applications. Food preservation is one of the most important applications of pulse electric field. Well, you can find now even the commercial juices that were treated with pulse electric field. As a result of PEF, if you understand, let's say, the process electroporation and the continuity of the cell membrane is lost, you can destroy the vegetative microbiota, inactivate them. So PEF, of course, without combination with more severe like heat treatment, doesn't give you the same possibility to achieve the same technological effect as traditional thermal treatment like pasteurization, but it allows extending the duration of the logistic chain. So this is huge benefit, because without any, like say, major changes of the quality of food. So you can try to sell, let's say, the product with very nice high quality, similar to fresh juice, but you have more time to do it. Another very important possibility that PEF creates, and this is, I think, the major now client, let's say, of the PEF technology, is it used in a broadly understood potato industry. So the PEF applications allow you to reduce the cutting force of potatoes for the French fries. Thanks to this, the knives, let's say, can be sharpened less often. Another very nice thing that reveals from the PEF application of potato is that they will absorb less oil during frying, which is a win-win situation, yeah, because consumers win, they don't have such a fatty French fries, and produce an enhancement and improvement of extraction. And by that, you can improve the extraction of many bioactive compounds, like some of food dyes, for instance, beetroot red, which is really important in food industry. Almost everything that is red contains beetroot red. And you can see that some of the research shows that you can increase the extractability of those pigments, bethanins, by over 300 and vulgaxanthin by nearly 150, which is, I would say, really nice. What is also interesting that by changing the parameters of PEF itself, you can shape the color. So you can shape the fractions that are extracted from the material. nice applications, especially I believe close to the student's heart. Enhanced color of wine. So you can use PEF to enhance production of wine. You can make it healthier, if you can say something like that. You can increase the anthocyanin content. You can increase the you can make color better. And a part of that effect that you can see here in this slide, PEF can also increase the efficiency of the pressing of the mast. Here you get some examples of PEF treated and untreated wine, both red and white. So, well, they are both good, I would say. As I mentioned, thanks to the application of PEF before the pressing, you can increase the efficiency of juice pressing, or you can try to reduce the enzymatic maceration time, or you can just eliminate that process, which is also beneficial because you don't have to spend money for enzymes. You don't have to waste time to do that. You can do just more. Of course, it's not like it's always like that. It depends on the process that you have. The research in this field showed that it doesn't work with all, let's say, type of presses. In some cases it does, in some other not. I think that it's a different story, I would say. Beside of the process kinetics, you can also shape the properties of juice. So here you have some examples how we can increase, for instance, total carotenoid content, or how we can increase the vitamin C content in juice based on the red bell pepper juice. You can modify the turbidity, so you can just allow people to have what they really want and what they need. Of course, if you will apply too high energy, you can overdo. You can overtreat the product, and you will have the product which is worse than it was at the beginning. So this is where the major role of the scientist is, yeah, to look the optimization of the conditions. Yeah, freezing. I was thinking, should I put this slide here because we have such a good specialist. You can use the pulse electric field in combination with some cryoprotectants, as demonstrated by the Lund team and Federico, to achieve very nice preservation of frozen thawed food. You can increase you can enhance, let's say, the process kinetics. I will not talk about details. I'm sure that Federico knows more about that than I do. So during the break, please go and poke him. And let's move to drying, because this is also why we are here, and the applications of pulse electric field in drying. So just to have overall picture of what drying is, I'm sure that we all know what it is, but it's one of the most important and popular food preservation methods. In fact, it was studied and applied by Native Americans, let's say, many years ago when they did pemmican, for instance, which allowed them to survive winter. So this is the oldest food preservation technique, I would say, next to freezing for sure. This is one of the best methods to handle with the surplus of crops. But this is also the most energy consuming process. Around 10% of total primary energy supply is consumed in the industry for drying. So it's really a lot. This is where we should think about, let's say, how we can make any additional, let's say, benefits. So if we will have a look at drying curves and drying progress, we can distinguish two stages of drying. So the first stage, which is characterized by the constant rate of drying. And this process, let's say, is proceeding with the same dynamics, but after some time, there is a specific point, a critical, let's say, value of water content when the drying is a bit slower, and it becomes slower and slower. So we consider this as a second stage of drying, where the rate of drying is constantly dropping. So there are a few strategies that can allow, let's say, to cope with that problem and to intensify drying. In the first stage of drying, it's super easy.
Yes.
Okay.
Yeah.
Now I see me.
Yeah. Just wait for it to restart. Just have to.
So how do you think how we can this is I'm teacher also. So how we can enhance drying in the first stage? Any volunteers? Kasia over there. Sorry. Yeah, but I don't see I see myself here. It's so pleasant still, but
Yeah, you need to show.
yeah, okay. Yeah, thanks. So it's easy. to intensify drying in the first stage, it's really easy because you can just change the air humidity, you can change the air temperature and airflow rate. But usually when we deal with food matrices, first stage is super low, super short. Some people say that they don't believe in the first stage of drying. Yeah, some scientists say something like that. So when it comes to the drying of food, second stage is the most important. And this is not so easy to be changed, yeah, because this depends mainly on the properties of material. And the presence of cellular structure is the real reason. So the presence of cell membrane, the presence of vacuoles, the cell wall somehow is the real reason why the second stage of drying is like a dropping phase, dropping rates drying phase. So if we could modify the cellular structure, and we know that we can do it by PEF, so we will destroy the cell membranes, this means that we can help here. And by destroying the cellular structure of food, we can accelerate the process. Yeah, so also the traditional one. So here you see our research that showed that we can reduce drying time of mango by even 50%. And at the same time, you can see that the structure and the color retention will be pretty good. If you will have a deeper look, then we can say that properly selected parameters can enhance also the quality. Total carotenoid content, yeah, it's important, I would say, factor when it comes to yellow and orange stuff, can be increased. In fact, you can also overdo, and if you will apply too much energy, you will have worse quality. Yeah, it's not like it works always. So you see that vitamin C content is a bit lower, but still, if you will have a look about and you will think about dried food as a source of vitamin C, you should, I think, try to seek for a different source of vitamin C. It works also with freeze drying. So freeze drying is super long process, super expensive process. Our research showed that we can reduce the drying of strawberries by 40%, and we will reduce the water activity of the material. Yeah, the appearance of freeze-dried product is something that very often is highlighted. Yeah, so here you have some fresh, here you have freeze-dried. They are also still good, and this is PEF-treated freeze-dried. So it's astonishing. When we had a talk with some guys from industry, they said that nah, it's too artificial. No one will buy it. We need to work more. So we did some industrial trials, and we found that crunchiness is also better in the case of freeze-dried strawberries, and crunchiness is super important parameter for freeze-dried product. Our micro CT scans showed, let's say, that yeah, the porosity is the real reason why we have those difference. Once again, if we will try to find out the real reasons about that, then Federico should probably help, because this is about dry. In my opinion, it's about freezing. So it was confirmed in the literature that electroporation works with drying. So one may think, let's say, what new can be done here? And it's always, of course, a room for new things. It was confirmed that irreversible electroporation works very nicely. But what about reversible electroporation? And there are only few works, in fact, all from this area, let's say, or from the Lund team, I would say. And I think that we will hear today a bit more about the reversible electroporation of basil and how it can help. So we will have some more insights in a moment, I believe. Yes, am I right? I'm acting as a chair now. Sorry. So I will leave you without the conclusion, because this is, let's say, maybe not the presentation for the conclusion, but take-home messages. PEF, is it the magic wand of the food industry? Is it the game changer or is it not? I think that we will have the answer at the end of this process. Thank you.
So now I leave the word to you, Grant, and the microphone.
Yeah, the microphone, the magic microphone.
The magic microphone.
Oh, I feel the power.
Yes, you should.
Okay. Yeah, I can do it. Yes. Okay. Thank you. Okay. Whew. That was really nice presentation, and Okay. I may not need to say anything because that's covered everything already. That's really nice. Thank you, Arthur. And let's start with mine. Let's start with the question, the last question. Is it the magic one? It is, but you need to know the spell.
Ah, that's
Yeah.
nice.
Okay, let me grab the water real quick. Okay. Okay. I prepare a lot of script and I hope that I will not miss one of them, but if I miss, you don't know, so it's fine because the script is here. Yeah. Share the screen again. Okay.
We missed it during the.
It's good now? Okay, nice. Okay, good morning, everyone. My name is Grant. Today, I would like to present my thesis, the reversible electroporation of Thai basil leaf as a pre-treatment prior to drying. As you know that I work mainly with the reversible part of the electroporation. So before we start, I would like to announce that similar to other papers in the thesis, now the paper 4 is already published. Yep. And then, okay, let's go. That's all. And as you may already know that in the thesis book that you have in your hand right now, mostly talk about herbs drying because, you know, from Arthur that drying is probably the most popular and the oldest method. And it's also true for the herbs. And it can be used to increase the shelf life of herbs from like 2 to 3 weeks to a couple of years, because I know that you forgot your oregano in the kitchen for many, many years already, but it's still quite handy to have it in your kitchen. Yep. So, however, I mean, even though that is quite convenient, but it's always a catch to the dry herbs, because most of the time, the drying causes the quality degradation. So it turned this beautiful plant, this is the basil, Italian basil, to somewhat like dry grass you may see here. This picture is actually taken from my supervisor. He bought the dry basil from the store and take the picture just to show everyone that how bad it looks like. And yeah, I think he made a point. Even though that the aroma of the dry herbs or this basil is still there partially, but I mean, it's not comparable with the fresh herb, of course. So if we talk about the quality, we may talk about 3 main things: rehydration capacity, color, and aroma. However, during the drying process, you see that we use a lot of heat as Arthur referred to that. With the heat, it actually causes tissue to collapse. So it means that rehydration capacity will not be there, or even like it will be reduced. And the chlorophyll degradation will occur. So the color will also be degraded. And if the stomata are damaged, then the dry herb will also lose its aroma. So this is problematic. So with this in mind, if the drying damage can be reduced, we might be able to get more fresh-like product, right? We might be able to minimize the color and aroma degradation, and we also could restore some viability of cells after the rehydration process. So that's make us the aim of the thesis, is to use the reversible electroporation as a pre-treatment to reduce drying time, reduce tissue collapse, and reduce the cell damage. And to achieve this aim, we have been studying, experimenting, and published 4 papers. In paper 1, we review the current state of pre-drying and drying method that is available in the literatures in the recent year, so that we try to find a gap that we can fit into and contribute the knowledge to the field. And then in paper 2, we established the best protocol that we use further in paper 3 and 4. Then in paper 3, we investigate the effects of the protocol that we just had in paper 2 on the cell damage and metabolic consequences. Then lastly, in the paper 4, we also investigate the effects of the protocol compared between vacuum drying and convective drying. And also we investigate the trichome integrity, which I will explain later how it's important. So let's start with the paper 1. So in paper 1, we found that to improve the quality of dry herbs, pre-treatments such as pulse electric field has a great potential to increase both efficiency and the quality of the dry product. And the pre-treatment that we review in the paper 1, for example, like blanching, ultrasound treatment, and pulse electric field, of course, we found that among all other treatment that we review, pulse electric field is probably like the most suitable option for drying of herbs because it has short processing time, low energy consumption. It can also be used in continuous process. And also there's still a limited industrial application to this one. So as Arthur already mentioned that PEF can be categorized into 2 types based on the viability of the cells after the treatment. The first one, the irreversible, it's actually good for the drying because it can drastically increase the drying rate and shorten the drying time. But the thing is that the quality might be degraded if you overdo it, right? So in reversible electroporation, it might not as effective as the irreversible one in terms of increasing the drying rate, but the quality will be remain because the cell is still alive pretty much. So in this thesis, we were able to use the reversible electroporation to improve the drying rate of Thai basil leaf. So now let's talk about how we did that. To understand how we use reversible electroporation to improve drying time or improve drying rate, we need to talk about a special structure on the leaf surface, which is called stomata. The stomata is a structure that plant use to control the gas exchanging rate between the leaf and its environment. It consists of 2 guard cells that you can see here in the kidney shape. The stomata will protect the plant from losing the moisture during the dry conditions in nature. So if you think about that, when we dry the herbs, this structure is actually the one that's responsible for the slowing down of the drying process because it is the natural protective mechanism of the plant. So let's imagine that if we could somehow inactivate the function of the stomata, we could be able to get faster drying rate, right? A work from our research group, COW, in 2016 has proved that if we electroporate the guard cells of the stomata, here, the guard cells, this will inactivate the function of the stomata to be closed, so they will stay open all the time during the drying process. Means that we can have a faster drying rate, and it means better quality, color, and aroma. So that was the paper 1. Now we know that PEF might be a suitable option for improving dry herbs quality and efficiency of the process. And in our case, reversible PEF seems to have a great potential to do it. So the next step is that we need to find a PEF protocol that can be used to achieve the reversible electroporation and the guard cells electroporation, right? So we did that in paper 2. Before we moving into the result of the paper 2, this is the typical micrograph that you will find further in this discussion. This is the surface of the electroporated Thai basil leaf under the microscope. This is using propydium iodide staining method. Because normally the propydium iodide cannot penetrate through the cells. So when we electroporate the cell and we create pores on the cell membrane, propydium iodide can get through the cell and stain the nuclei. So you can see the red dots here and there all over the place. These are the nucleus of the cells. With this method, we were able to tell if the cells are electroporated or not. And another one, we also talk about the reversible electroporation. So we need to test for the viability of the cells. So we need to use the fluorescein diacetate, which is FDA here. In short, if it's green, it's alive. If it's black, it's dead. Okay, and this is what we're actually looking for in our sample. So we want to have the electroporated nuclei in the guard cells, which you can see here, 2 of them, because there's 2 guard cells, so 2 nucleus. And the stomata should be open after the electroporation, which you can also see here is a little bit more bigger than this one. Yeah. And this is just the range of the parameter that we test. We have voltage, the pulse width, pulse space, polarity, and number of pulse. We test all of this. And also in the experiment, we measure the resistance, electrical resistance of the treated leaf. So if you imagine that if we electroporate the leaf and then we create pores on the cell membrane, something will leak out of the cells, and then it may contain ions. So that will decrease the electrical resistance of the tissue, right? So we measure the electrical resistance, and then we calculate the electrical resistance ratio and plot it against the number of pulse that we apply. So you can see that when we increase the number of pulse, the electrical resistance will decrease as the electroporation goes. And this is how we know that it's electroporated. And from this chart, if we take a look at each point of this chart, the story that I'm going to tell you right now is the changes that we see on the leaf surface when we increase the number of pulse applied to the sample. When we look at the first point, it's expected that we will not see any electroporation because we didn't apply any pulse, and the surface will look pretty much like this. So you can see that it's red, yes, but there's no electroporated nuclei. And then when we increase the number of pulse just a bit more, like to 25 pulse here, you will see that there was some electroporated nuclei. You can see it in the green circle, but it's not what we want because it's not homogeneously, right? So we increase it even more. This is 100 pulse. Then we find homogeneous electroporation. This is good, but however, this is still not what we want because we want to have guard cells electroporation. So if you take a look at the guard cells, it's super small here. And yeah, you can see that it's not electroporate, right? So we need to go further. This is 125 pulse. We started to see that some of the guard cells start to be electroporated, but there's only minor of them is not homogeneous at all. And then if we increase even more, there will be a point where the guard cells are electroporate homogeneously. And you can see that like the guard cells, most of them are homogeneously electroporated. And this is what we want. This is what we're looking for. So now we know that we can electroporate the guard cells, but how about the reversible? If we increase the number of pulse a bit more to 300 pulse, we can still find that the sample is pretty much alive. If we take a look at the surface, it's still green. This is 300 pulse. And this is the viable range of the electroporation that we can work with. Because if we increase the pulse even more, on the surface, it will look pretty much like this. You're supposed not to see anything here because yeah, it's supposed to be dead. And yeah, so this is to sum up. You can see that here, point B, this is the point where we found the homogeneous electroporation without the guard cells electroporation. And at point C, we found that this is the point where the guard cells are homogeneously electroporated. And this is the gap that we can work with. Because if we go further, it will be irreversible. If we go less, the guard cell will not be electroporated. So the gap here is quite narrow. And we will use the protocol that we found in this gap in paper 3 and paper 4. So, but the paper 2 cannot be completed if we don't really test the protocol, if it's actually working. So this is a drying curve of the reversible electroporated sample. You can see the control. And the second one here, that is not so different from the control, that is the reversible electroporate Thai-Basil leaf, but without the guard cells electroporation. But the one here, the bottom one, the fastest one, is the one with the guard cells electroporation. So you can see the drastically different here. So The new finding in paper 2 were that the electroporation, it is a progressive process. It's not like a light switch that you can turn on or off. The gas cells require higher number of pulses to be electroporated, that we know. And increasing the number of pulses further from the point where the gas cells electroporate might kill the tissue. And the gap between the gas cells electroporation and the death of the tissue is quite narrow in general. And ultimately, we found 6 protocols that we can use to reversibly electroporate the tuberous leaf and also the gas cells. So you can find the details of these 6 protocols in the thesis in your hand. So that was the paper 2. Let's move to paper 3, which we test the effects of the PEF protocol that we just had in paper 2 on the cell damage and metabolic consequences. So let's start with the treatment that we have in paper 3. In paper 2, we already have the electroporation. So we have 2 options here, to electroporate and not to electroporate, right? And then in paper 3, we add one more step after the electroporation, but before the drying process, which is resting. The idea here is that if we allow some time for the tissue to recover, it might be able to recover from the stress that they got from the electroporation. So that will give some more chance of the cells to be survive after the drying process. So that makes us 4 different treatments: PEF rested, PEF, control rested, and control. And then we dry the sample from these treatments and with convective drying, and then we rehydrate them and analyze them for the moisture ratio, moisture content, rehydration, conductivity, and photosynthesis and respiration. The first result, this is the thermal power or the heat that produced from the tissue during the resting process. So you can see here that the PEF treated one has somewhat like 2 to 3 times more heat produced during the resting process. So this means that something definitely happened during the resting process that elevate the metabolic activity of the tissue. Yeah. And then for the drying test, we can see that the slowest drying sample was the control rested, followed by the control, and then the PEF rested, and the fastest one will be the PEF without the resting process. It seems here like that the resting process increased the drying time just a little bit, but anyhow, the PEF rested one was still faster than the control. And then we chose the sample from the moisture ratio of 0.1 and 0.2 for the further investigation, which is, the first one is the rehydration capacity. So after we rehydrate the sample, you can see that the biggest difference in the rehydration capacity is between the PEF and the PEF rested sample. If we think about that, the only difference between these 2 samples is the resting process, right? So this result implies that the resting process helped reducing the tissue collapse and increasing the rehydration capacity, which is one of the most important quality of the dry herbs. In fact, if we take a look at the rehydration capacity of the PEF rested sample, in both moisture ratio, you can see that it has the highest one among all other treatments. Now, when we measure the photosynthesis and the respiration capability, this measurement was not only tell us that parts of the functionality of the cells are preserved, but also tell us that how well it functions compared to each other treatments. So we can see here that control and control rested samples show quite low respiration and photosynthesis. And the PEF only without resting is even worse. So it means that PEF only will kill the cells, definitely. And while that, when we compare to the PEF rested sample, you can see that it has highest photosynthesis and respiration rate. And for the moisture ratio of 0.1, you can see that all other samples are pretty much dead because they are not respiring, they are not having the photosynthesis. But the BEF rested samples still show some respiration, means that some cells were alive and respire after the rehydration process. With all the evidence that I have shown, it points that BEF followed by resting process decrease the cell damage during the drying process. But we also have some other evidence in the paper, such as that, sorry, I need to take a sip. Okay. Oh. Such as that, BEF rested samples show the less ion leakage, or the electrical conductivity is low compared to other treatment. It means that less ions leak out from the cells, and also it shows more viable cells on the leaf surface. You can find the picture in the thesis book. Yeah, so that was paper 3. Now we know that BEF rested show its effects to decrease the cell damage significantly compared to other treatment. Now in paper 4 that has just been published, we compare these effects in convective drying and vacuum drying, as well as we also investigated trichome integrity. I will talk about trichome later. And let's start with the difference between the treatment of paper 3 and paper 4. First of all, we know that BEF without resting is the worst. It kills the cells, so we exclude that treatment from the paper 4. Secondly, we add the vacuum drying as a comparable drying method in the paper. And then we analyze some more aspects like color and trichome integrity. And also, we add one more moisture ratio to work with, which is the moisture ratio of 0.05, which is the completed dried sample, like the commercial one that you found in the store. Okay, the first result is the photosynthesis and respiration capability. As you already know that BEF rested show the highest value here in convective drying. In vacuum drying, it turns out that all the samples show low respiration and photosynthesis capability. This result suggests that the vacuum drying might damage the tissue more than convective drying. And the protective effect that we got from the BEF rested could not protect the cells from this damage. And in the moisture ratio of 0.05, there was no respiration and photosynthesis occur in any of the samples. So it means that it's dead. And this can be confirmed by the ion leakage or the conductivity of the rehydration water, that we can see that the vacuum dry sample has significantly higher conductivity compared to the convective dry sample. Means that more ions have been leaked into the water during the rehydration process. And so now we know that BEF rested could not be used to protect the cells in complete dehydration and for both drying method and in any levels of the vacuum drying. So what's the point of doing it, right? The answer lies in this picture. We found that the special structure on the leaf surface called trichome. This is the structure that stores essential oil on herbs. The integrity of the trichome is crucial for the dry herbs to maintain its aroma. And unfortunately, trichome usually will be destroyed during the drying process. You can see the trichome here in the red circle. Normally, to study the trichome is quite a tricky process because it has quite complex sample preparation process. However, in this paper, we were able to look into individual trichome, and it looks like this. Oh, it's nice. every time. Okay, in this experiment, we use the 4K high resolution microscope to investigate the trichome because it has no sample preparation needed and it operates really fast. You can just put the leaf in and then take a look at the trichome individually. And it has really high resolution. And so when we take a look at the fresh leaf first, you can see the intact trichome will look pretty much like this. And we also found the damaged one, which is normal in the fresh herbs. You can see the difference in size and shape of both of them. And then if we take a look at the rehydrated product, you can see that the color of the trichome changed a little bit. This is due to the chlorophyll degradation and things that change the color. And we also found another type of the trichome, which is destroyed, completely destroyed trichome in the drying. This is the proof that the drying can damage the trichome, and it's so clear. So to analyze the integrity of the trichome, we actually measure the size of the trichome that we found on the leaf surface using the fancy microscope that we have. And we can see that here that in the table, the PEF-rested samples show the similar average size of the trichome to the fresh leaf, actually, while other samples show much smaller size of the trichome. The vacuum dry sample show the smallest one of the size of the trichome, but the PEF-rested vacuum dry sample still show significantly larger size of the trichome compared to other treatment. So the new finding that we got from paper 3 and paper 4 is that the resting process allows some cells in Thai basil leaf to recover, although it's not in the completed dry product, but somehow we can protect the cells during the drying process. And also the vacuum drying causes more damage to the cells. And also PEF-rested can be used to preserve the integrity of the trichome of Thai basil leaf in both convective and vacuum drying. So that was paper 4. So now let's conclude this thesis. Just a bit recap to the aim that we want to use reversible electroporation to reduce the drying time. We were success to do that because PEF as a pretreatment can provoke the stomatal opening and facilitate the drying process. And the second part that we want to reduce the tissue damage and tissue collapse and cell damage. We found that resting process allows some cells to be viable after rehydration, but I would say yes, but there's some limitation because this is only evident in partially dehydrated leaf, which is moisture ratio of 0.2 and 0.1. And another one is that in the fully dehydrated leaf, even though that we cannot save the viability of the cells, but the trichome is protected. So the conclusion from each paper is like this. The paper 2, we found that the electroporation is the progressive, right? And the GAR cells require more intense parameter to be electroporated. The gap that we can work with is quite narrow. So you need to find that gap for each type of herbs. And the resting allows some cells to be viable after the rehydration process. And vacuum drying causes more damage to the cells. So for the future outlook, I think it would be interesting to find that the details of the protective mechanism that we got from the PEF-rested, like how it's working, so we can maybe expand that effects. And also we want to have like a compare to the different drying method and some more other types of herbs, and also the aroma quality and aroma compound analysis would be needed because we preserve the trichome. Now we want to know that if the aroma compound is still there and the quality is still there. So this research is financially supported by Royal Thai government, and this is our collaboration. And thank you for your attention. Okay.
So thank you, Grant. And we will take a short technical break, 5 minutes, so everyone can be back at 10 o'clock sharp. And then we will continue with the Q&A session of this thesis defense.
Jag tror ni kan flytta på er lite grann bara.
Nej, jag tror inte det. Jag kan fixa.
Jag vill ha den för det är precis som...
Den här är på.
Ja. Vi stänger av den så länge.
Så,
So I would ask the audience to take the places, even if we will wait till everything is okay, but I think we should take.
Even though it was USSR.
Varför stänger vi av den nu? Därför Grant kanske vill använda bilder därifrån sen. Men skitsamma. Yeah.
Should we put this on?
Yes.
Okay.
You will have one when I. So I think the people here will take their places and we will restart. But before we restart, I will present the most nervous person in this dissertation, because I forgot to present them. And that is, of course, those that have no role whatsoever today, but had a very strong role leading up to today. And that is Grant's supervisors. And Grant main supervisor has been Federico Gomez, and his co-supervisor has been Ingegerd Sjöholm. So, as I said, this is the day when they rest and Grant works. So I will get Grant to work now, because we will start the questions and we will start the discussion. And here, Grant, you have.
Thank you. Okay, sounds good.
Okay. Me too. I'm good as okay. So I should start, I believe. Okay, so before, let's say, we will move to the discussion, I would like to emphasize that I really appreciate the amount of work that has been done by you, and congratulations on the fourth paper that has been published. So yeah, it should be, I think, emphasized that it's 4 papers, all are published in well-recognized international journals. All of that was already peer-reviewed. So we are here just to have a talk because everything was already done, I would say. Critical reviews in food science and nutrition, IFSET, bioelectrochemistry, applied sciences, all well-recognized journals. So really congratulations on that.
Thank you.
To you and to your supervisors, of course. I really appreciate that. So before, let's say, we'll move to the path-related thing, since the first paper was more about, it was a review paper, yeah? Where you have, let's say, put the background of the drying methods and put the background of different pretreatment methods. When I think about drying of herbs, I usually think very traditional processing methods. So could you discuss a bit, let's say, how those methods that you have discussed, that you have presented over there, could be like economically and environmentally and from quality point of view justified when it comes to drying of herbs?
You mean the drying process that
yeah.
they
So
usually use in the, yeah, I would say that the oldest method that I know that they use from my experience is a shade drying, I believe, that they just hang the herbs in the kitchen, basically, so no exposed to the sun, and then leave them for the moisture to leave out the tissue. And in the one that we use, we decided to use the convective drying because we think that is the most popular one in the industry because it's such a simple process, right? I mean, to do it, but the details of it, of course, there's a lot of tricky things in that. But yeah, convective drying is probably the most popular one, so that we shows that. And yeah, we actually reveal quite some of the drying method in the paper one that we found that is quite interesting, actually, that might be in the future that we want to work with them. Yeah,
okay,
so.
And what about those pretreatment methods? You have presented like the new one, let's call the new one, like ultrasound, pulse electric field, that was subject of your study.
Yeah.
but also blanching. So how you would position, let's say, the pulse electric field treatment in comparison, for instance, to blanching, because usually we know why blanching is performed. Yeah. So, and I think it's really important when it comes to processing of raw materials like herbs. Yeah. So blanching we apply mainly to inactivate enzymes and to do the things like that, to evaporate, to remove air from the tissue. And when I think about drying and herbs drying, as you have also studied, is usually conducted at very low temperature. Yeah. And the processes are long because of the low temperature. Yeah. And the processes last for a very long time. So how you would position, let's say, the role of PEF here in comparison to blanching, for instance?
Yeah. Let me think about that a little bit. I think I reviewed the effects of the blanching. It's actually come from the paper from one of my colleagues in Thailand. Actually, he succeeded to use the blanching to increase the retention of the color of herbs. But the thing is that in blanching process, they use like quite high temperature. Yeah, like 80 degrees or 90 degrees even. And the problem that they face now is that the aroma is not really there. So they actually work for like the herbs for the bioactive ingredient as a bioactive ingredient. But here for the basil, we actually think about the aroma. So if I would say that PEF could be used, PEF is a little bit more suitable in terms of the heat that we use, because in PEF we don't actually utilize heat. So if we can compare the PEF and the blanching, I think PEF could be better for the aroma if the aroma is the aim for the.
And what about color, for instance, and the protection? Because based on the results that you have, let's say, published in the paper that was already published, now published, there is a nice, let's say, that the total color difference, for instance, there was no differences at all, I would say, no statistical significant difference. So if we can say that PEF from the wine point of view can protect, let's say, the aroma, and I think that we will discuss it as well in a moment, then what about the color? Because why I have asked you about blanching? Blanching destroy enzymes, and enzymes are the main reason for the color changes during drying also, because we have still, let's say, the process lasts for a very long time. So the product is in a mediocre, let's say, and high water activity level for a very long time, which is a very nice conditions for the enzymes. So what is the effect of PEF on enzymes here? How do you think? What's your opinion? It's not like...
Yeah, I mean, I'm not really sure if PEF will change anything on enzyme. I'm not really sure because I didn't do any research on that. But as from I see from the sample, I think the color is still quite preserved actually. Yeah, but I mean we didn't take a look deep into that. Why is that happen? But one of the possible reasons might be the shorter drying time, of course, because heat will destroy the chlorophyll. Yeah, and I mean. What was the second part?
No, it's okay. I'm like, so there is a room for the research now, that we could study the enzyme like chlorophyllases that is degrading the chlorophyll during drying. Yeah, cool. So the process that the pretreatment that has been used in your study, let's say. It assumes that the Gwart cells will be irreversible, irreversibly electroporated, so the electroporation of Gwart cells was irreversible, it was not reversible.
I mean, we take a look at I take a look at the reversible part in terms of the viability of the whole tissue. So,
but those were like totally destroyed, so that's why they didn't close and open, or?
That's actually a nice question, because I think I don't have the answer like in the top of my mind, but if I can think about that, like all other cells, it should be reversible. So in terms of the reversibility, I think the gut cells will also
Reversible.
be reversible.
Okay.
Yeah.
Okay.
I mean, that's my case. Yeah.
And so because when you have presented, let's say, and described it in your thesis, you talk about different parameters, of course, that will influence the type of electroporation. So we can talk about the product-related parameters and the process-related parameters. So how do you think which of those parameters would be the most important that can cause, let's say, or we can connect them afterwards with the effect? So which parameter will be the most important from product and process point of view that will cause the proper type of electroporation?
Yeah. So, I mean, I work with 5 different parameters, and all of them actually have an effect, but some of them, like voltage, is actually really important, because I found that less than 600 volts, the gas cell will not be electroporated at all. Yeah, and so that's why we use 650, and pulse width actually important, because too short, it will take a lot of number of pulse to electroporate the gas cells, and to the level that it might not be reversible anymore. So yeah, I think pulse width also important, but for the pulse space, it may be a little bit less important, because I found that there's quite a huge gap in that parameter. We can work with 300 microseconds to 700 microseconds without any difference. And the number of pulse, of course, really important, because that is define the gap that we can work with. And yeah, the gap that we define in the thesis is actually based on the number of pulse. Yeah.
Okay, and yeah, because maybe I wrongly at the very beginning, let's say, understood that the GooGrant cells will be like irreversibly electroporated, and but are there any product-related factors that will influence also the progress of electroporation?
The product, from the product standpoint, I think first of all, you need to have gas cells, of course, to use this method.
So you need to have leaves.
And there's one recent thing that I actually try to looking for, is that the difference in the gas cells between the monocot and dicot, actually, because it has different gas cells. So I'm not really sure if the herbs with the that is monocotyledon, it will work with this method. I'm not really sure, but it would be interesting, because we have a lot of herbs that actually like in the monocotyledon, like lemongrass, like that. Yeah.
Okay. I was just also thinking, because from those parameters that you have tested, and it was really like a lot of parameters that you did, like a lot of protocols, that was really nice. It was not so easy to follow. The presentation helped me a lot, to be honest, when I have seen the arrows that, picture, graph, it was super cool, super good. It facilitated my work a bit. So I was just curious, let's say, how those parameters that you have tested, you wrote that the polarity has had the big impact, let's say.
Yeah.
Could you try to explain it? Why we observed so huge difference? Because it was the only parameter that had, let's say, influence on guard cells, but it didn't have any influence on epidermis, if I remember it correctly. So it was the only parameter, let's say, that had the difference was stated. So why it was like that? Do you have any idea? Or
yeah, the effects of the polarity that I found is that the bipolar pulse is not as effective to electroporate both epidermal cells and the gas cell. In fact, I didn't find any gas cells electroporation using bipolar.
Why so? That's what I was like thinking about that. So.
I mean, if we take a look at the gas cells, when we use the monopolar, it's already require higher intensity of the parameter, like more number of pulse, more voltage, more pulse width. And then I think with the decreased effectiveness of the bipolar, I think I just didn't go far to that point that think I'd be really quite far from what the range of the parameters that we already have. Yeah, so basically I didn't try to go that far with bipolar because in the range of other parameters that I test, the bipolar didn't get it.
Okay.
Yeah.
Now, that's very interesting, I would say, because we know very well, let's say now, what is the impact of different processing parameters on electroporation. We know that electric field intensity, as you have mentioned, play roles, very important role. We know that dimension, cell size is very important factor from the product point of view, yeah. But still, this polarity thing is very open, and I was curious because I don't know the answer, to be honest, on that point. And I think that this is a very good idea if you will try to pursue, let's say, those electroporation issues, let's say, in future. That would be nice to give the answer. What is the polarity, the impact of polarity, and why it's like that? Yeah, this is to understand the process. So you also said that when it comes to this reversible electroporation, and then there was this resting period, yeah?
Yes. And
from my perspective, what I think, let's say, I'm a food engineer, so I think about the applications as well. And that resting period lasted like 24 hours. If I'm, yeah. So two questions that I have. So what about, let's say, industrial application of such a, he's smiling, so I think that I took his question now. What, let's say, that the consequences for the industrial application of the process? This is the first part of the question, let's say, or the, let's say, discussion. And another is that I'm not sure how it works here, but in many countries, the microbial quality of herbs is not good. Maybe not those that are packed in small pouches, but if you buy a bulk one, that's a problematic stuff. So that's why they are often, we call it like hygienization process, where they use the steam, for instance, to destroy microbiota. And when I think about the resting period that lasts 24 hours and it is conducted in humid conditions, I see the perfect conditions for deterioration. From microbial point of view, do you think that this could be controlled somehow and managed, or maybe it's not a problem from your perspective?
I mean, it's definitely going to be a thing that we need to concern when we produce herbs. Of course, even that the dry herbs can be stored without a problem because the water activity will be super low.
Yeah.
But the thing that the material, the microorganism that infected into the material is definitely be the thing that we need to concern. And yeah, that will be a challenge, I think, because to use PEF, we need to submerge the leaf under the water and pass through the pulse. There will be a concern, of course. I'm not really sure, like from the manufacturer perspective, how to fix that, but interesting. Yeah, that's
but I mean, like, is it a problem from your, how do you think, if you would be a processor, 24 hours of,
I think I have discussed with Federico actually about the manufacturer here in Sweden that they didn't use PEF, but they used the low drying temperature, which is 40 degrees Celsius, and they also like want to get rid of the problem of the microorganism. So, but the thing is that they produce in small batches, so they can control the sources that come. That's one thing.
The best option to control the source. Yeah.
And another one is that they freeze the sample after the drying process.
After the drying.
Yeah. So they could kill all the microorganism. Yeah, with that.
That's very expensive then product.
That's very expensive.
Both very expensive processes. Right. And do you think that PEF can, because we know that PEF can kill the microbiota, yeah? Do you think that the parameter that you have worked with can kill also, can be somehow
I'm not
helpful
really
here?
Yeah, I'm not really sure about the resistance of the microorganism, but I would say that no, in the level that I use, definitely not gonna pasteurize or not gonna
Yeah.
heal enough. Yeah.
Of course, that's a good that's a good answer. they cannot too low voltage, yeah. But you can try to think. Let's say if you want to play a bit, you can try to use PEF to control, let's say, the water that you are using, let's say, for the resting period. And when I was thinking about that resting period, you wrote over there that it was performed in a dark conditions. Is there any particular reason why it requires dark conditions, or I'm sorry, just curious because
I mean, at that time, I think what we have thought about that is we want to have it in the like let me think about it a little bit, because I need to think about why I did that.
Maybe there was no reason.
Yeah, I mean, definitely I need to control the rate of metabolic activity. I don't want them to go crazy, you know, after like PEF, they already have the stress. So if we put it under the sun, it also need to do the photosynthesis thing, and also the stomata will be exhaustedly open because the light is turned on all the time. So yeah, I mean, think about that. Like normally the leaf will be in the night for 8 to 10 hours per day anyway. So I mean to control it, I think the idea was that, I'm not really sure. the idea was that we want to control it in one condition.
Okay.
Yeah, so we don't want to change the cycle of it. Yeah, so
that's wise, I would say. Yeah. And so I found that this resting period is really important. Yeah, when it comes to proper quality of drying and also drying kinetics. So you emphasized in your thesis that there is that the resting period allows the plant to restore, to rebuild, let's say, to reseal maybe the cell membrane somehow. Yeah. And you also wrote that there is some kind of a protective mechanism involved. Yeah. So do you think that this resting period allows also the plant to produce some secondary metabolites that will impact, let's say, and do you have any, let's say, maybe conception or anticipate what kind of secondary metabolites or what kind of products can be produced by the plant? Or maybe there's something else that is the explanation. Maybe it's not about the chemical changes that go on during the resting period, but there's another reason. So how do you think?
I think I don't remember it in my mind, but I think I have wrote something in the, let me check, in the metabolic consequences. Yeah. Here, like, I mean, I read the literature about the stress, and yeah, there will be here. Sorry.
No worries.
Yeah, the reactive oxygen species, of course, during the resealing, the resealing process. But the things that I didn't like do any how to say the biochemistry on the sample, which is quite interesting. If I had time, I would want to go to that, but now it's probably next student. but that's really I think that will be the key to understand what happened during the resting process, and that would be the answer why the protective mechanism is actually working, and that is still like the answer that we want right now.
But do you think also maybe some physical like physical reasons can be incorporated to the explanation? Like for instance, you showed us very nicely that PEF rested products and control rested product, the kinetics was a bit different. So the drying time of those products was longer, and you also mentioned that it's because in the thesis, that they gained a bit of water. So do you think that this could be also somehow the explanation of the differences that you have observed? Like if they will gain a bit more moisture, then the drying will, the temperature of the product will be a bit different. So maybe not only this protective mechanism is not only involves some chemical changes or enzymatical changes, metabolic changes, but maybe also it involves some physical. How do you think?
Definitely, when I rehydrate the leaf, I see that the water actually goes inside to the airspace, because we can clearly see that. And yeah, I'm trying to think if the water could.
I mean, why they have gained more water? What was the reason? Yeah, that they even before drying it, because before drying they also gained more water, I believe. Yeah.
You mean
after resting they have gained some water during the resting? Yeah.
Yeah, and I mean the reason for that is I think it's the natural mechanism of the herb itself, that when it has a lot of humidity outside, it will try to balance itself, so it takes up some.
Yeah, but PEF had more of that, or
PEF actually has more of that.
Yeah,
but I'm not really sure if I did the statistic on that. But yeah, so it's I mean, both of the control and PEF actually gain some water after the racing process, but I don't actually remember that PEF has more, but it could be because the stomata is open all the time, so it cannot control the difference in the, what is that, the vapor pressure.
Yeah, turgor. Yeah.
Yeah.
Okay.
Yeah. So they cannot control that, and the water that actually go inside. This thing I'm not really sure if it's will help with the viability, but I mean in the result that I have here is that the control reset actually show a little bit of the viable cells, but I mean it is not compared to the PEF reset, of course. Yeah.
Okay. That's also very, very interesting. Yeah, that like some maybe physical, because when I was thinking about that maybe there is some kind of a specific, like if water will go inside and it will be more of water, then the temperature profile during the drying will be a bit different, even though let's say the drying will proceed the same kinetics. It is possible because the dry and wet bulb temperature could be different. And it would be nice, to study that in the future, like from metabolic point of view, as you mentioned, this biochemistry, but also physical changes. So maybe some SEM analysis of the end final product could be also helpful to explain, let's say, the porosity. I like that microscopy that you have used. We have this also, but I would never think about this application. Yeah, never. It was so nice that you have measured the structure. We only make funny movies with microscopy. So that's the thing. But it was really nice that you have studied that. I think that I will have one question related to that in a moment.
Okay.
But since we are talking about the microscopy now, as I mentioned before, this presentation helped me a lot to understand, let's say, the processes that you have studied. And of course, this microscopic method that was utilized by you, and it's like widely accepted by many different groups to assess, let's say, the electroporation, type of electroporation with the fluorescent microscopy. It's very good, robust. It gives overall picture. One drawback: a long time, and requires the equipment, special equipment to have. Yeah? Like not all companies, let's say, have. So, and you also measured the electrical properties, so the resistance. And this is typical method, to evaluate the electroporation efficiency. But how do you think, from once again, like processing point of view, industrial point of view, is it possible to correlate somehow the electrical measurement with the type of the electroporation? Because as you have mentioned, the gap that you have, the processing window that you work with is very narrow. How can I know, can I use any rapid test to know that, okay, if I will have this and this efficiency of pulse electric field treatment as measured by electrical properties change, I will deal with reversible or irreversible electroporation?
Oh, this is a nice question. for the first one, if it's irreversible,
Mhm.
we can actually observe that like by our own eyes, because you're gonna see it's
Okay.
like collapse. Yeah, and the color may also change because the data, so it actually changes quite fast. Yeah, like within 5 to 10 minutes, you're gonna see the color change on the leaf if it's bathed by the electroporation.
Really?
Yeah,
Oh, okay.
yeah. I mean, at least in Thai basil and also Italian basil, you're gonna see
Mhm.
that.
And
Yeah,
why
but,
so?
I think because of the cell content that leaks out, that actually like maybe provoke the chlorophyll degradation right
Mhm.
away, and the chemical balance in the tissue will be messed up.
Okay.
Yeah. And but for the reversible electroporation, this is another thing, because the gap that we can work with is quite narrow.
Yeah.
That I mean after the electroporation, we don't see any difference like at all. It looks fresh. It may have a little bit of like will be a little bit softer right after the electroporation, but then it will come up like within
Mhm.
minutes. Yeah.
So to restore, yeah?
Yeah.
Okay.
So that one thing that I think we could use is just the bright field microscope
Mhm.
to see if the stomata is open.
Mhm.
Yeah, because that I mean, that's not gonna tell all of the story, but at least it's gonna tell that, okay, we electroporate the glass cells, because after the electroporation it will open.
Okay, so the electrical measurements will not tell us like a lot here, yeah?
Yeah, the electrical measurement, I'm not, I mean, I didn't do like, because in the industry we need to have like a standardized thing that we like check it and then go, right?
Yeah.
But I didn't check the specific the electrical resistance of the leaf. Maybe that there is some a gap that we can set. Okay, if we measure the electrical resistance of the leaf and it show this number, it might have that level of electroporation. Probably
it
working.
will show us the level of the electroporation, but it will not tell us if it's like reversible or based at least on what you have showed. Yeah, and that would be nice to have the method that could allow, let's say, us to say that very quick measurement based on electrical properties, and we know the type of electroporation. I was curious because maybe I could steal some of your ideas, let's say, and then do the same in Poland, because we don't know how to determine the type of the electroporation without the microscopic imaging, and that's a pity. Yeah, that's a very huge pity. Yeah, okay, and I will go back once again to those graphs because I really like that graphs. So you discussed mainly and I will also go back to one of my first question in that story. So you discussed, let's say, the impact of the number of pulses. From my experience, let's say, it's another parameter that is also important is a specific energy input, yeah, which of course will correlate somehow with the number of pulses. But is there any difference? I'm like, from your perspective, is it a number of pulses that plays role, or this is the energy input that plays role?
Yeah, actually, this question is actually come to me quite a lot about the specific energy, and
you put the specific energy input somewhere, but I remember, and there was some difference.
Yeah, some difference, and I think the major thing here is that, I mean, this is the way I look at it. It's like the herbs, I mean, different herbs, I believe that there will be the difference in the levels of parameter that you need to work with. For example, like in Thai basil leaf, I found that only like the number of pulse width of 50 microseconds and 175, right? So you see the gap there. Yeah, because I mean, because the things that we need to somehow balance the levels of parameter, like if you have this number of this amount of pulse width, you cannot go further like on the number of pulse, something like that. There is like some balancing things here. So I think if you want to use it in the actual production, I think we need to fix most of the the parameters and work with only one or two parameters, and then we need to have like a specific gap for that. So I would say that if I need to work with this in the future, I will just go with the number of pulse, yeah, to have the range that we know exactly. Okay, this is working for this type of pairs.
Okay.
Yeah,
better than because when I went through this pictures, yeah, from microscopic imaging, I was like, yeah, it's maybe also like the path isn't it's like the probability of electroporation. If I will apply only one pulse, then the probability is like, let's say 10%. Yeah. If I will apply more, then there's a higher chance that electroporation occurs. As you also mentioned, it's not one or known effect. Yeah. But at the same time, we know that a specific energy input is something which is easy to control. Yeah. Especially when we think about the industrial application, and it needs to be measured when we want to know if there are some benefits from, let's say, energy point of view. Yeah. So since I'm here about energy talking about energy point of view, so how do you think the energy consumption during PEF is much higher or much lower than the energy that could be consumed during the drying?
I think it's much lower, much lower. Yeah.
Okay.
And then because we apply the pulse in, I mean, if anyone that never worked with PEF, I mean, talking about 300 pulse, you may think like, no, but yeah, that's it. Yeah.
Okay. Okay. So it's a pity, but I think that we should agree with that we cannot develop any optimal protocol. Yeah. So this is the spell that you were talking about. This is the role of the scientist, to develop the
spell.
And do you think that at least we could try to develop some kind of a book of spells, like for basils, those spells are working, and for oregano, those spells are working. Is it possible, in your opinion, to develop such a book of spells?
Ooh, that would be challenging, actually. Like,
or is it like necessary to develop each time that I have my production line, I get a new raw material, I need to do the research from the very scratch in the beginning? It would be nice because it will give a lot of people a job, of course. Yeah, but what about money? Yeah, the industry guy is sitting over there and
Yeah, I mean, from my experience, I found that like even like the basil, like Italian one and Thai basil, they have quite a different parameters that need to be uses. But I mean, our role here is should be to find the effects or influences of each parameter and try to get the answer that's how that parameter actually affects to the material, and then I think with the let's talk about like with the same group of material, like herbs, like vegetable. I'm not really sure if they should have the guard cells, right? Yeah, the vegetable also, something like that. And if we can gather the effects of each parameter on each group of herbs, if we can categorize them, but I mean, we need a lot more works, of course, to know actually like what is the effects of each parameter. And if we can do that and have a book of collections of that will be helpful.
Okay.
At least for the starting of some company that they want to use this, so they can have like, okay, this is the effects of the pulse width, this is the effects of pulse space, so they can roughly try to come up with their own protocol and then try that and work from that. That will be helping.
Yeah, the only problem that I see with such a book being published, let's say, is the huge differences between the equipment that people are using. Yeah, and there is no standard PEV equipment now, and so some people are working with longer pulses, some with shorter. Sometimes you have different pulse shape. This will also impact. And so that's why I also asked so many times about the energy input, because electrical field intensity and energy input can be controlled let's say by different parameters, yeah. And maybe this could be somehow standardized in such a book of spell. Yeah, I even wrote that, you know, sentence. I put your name here, so I will cite you with my students in future. The results, let's say, that you have achieved when you have compared maybe like why you have used vacuum drying. Convection, I understand the reasons, let's say. Why vacuum?
Yeah, the idea was that I mean, I think about the drying process. Okay, if we use heat, that is what we want to avoid. So I was thinking about the drying process, that okay, we don't add external heat to it. So the idea is that I use the vacuum dry but at ambient temperature. Yeah, so the idea is that to basically give the basil more chance to survive.
Yeah, from one point of view, but for the second, you know HTST, so high temperature short time principle. Yeah. So a longer drying time can also cause some other problems. Yeah. Do you think that this could be also a?
I think, I mean when I look into this, the drying process, right? So I mean I don't have the information in my mind right now, but let's think about the high temperature. The problem is that the aroma will be
lost. Okay,
right away.
No, I'm just curious because vacuum causes the losses of volatiles
also.
And this is something that could be a negative, like a drawback of the process when you think about drying of herbs, which contain a lot of essential oils. Yeah, but the results that you have achieved, let's say, when comparing those the paper 4, the results that you had for convection and vacuum drying at the very first sight, let's say, they were really surprising. Because most people, they consider vacuum as you said, gentle processing technique. And but the explanations afterwards that you have, let's say, provided related to the mechanism of water evaporation and so on, and this is how you also explain the Trichomes collapsed. Yeah, but I had one question related to this Trichomes collapse. You let's say you told us that Trichomes are the structures that store aromas. But few minutes ago, you also mentioned that during or after PEF treatment, reactive oxygen species are formed. And that's true, of course. So how do you think, even though, let's say, we have Trichomes preserved, can we expect any changes of profile of the essential oil that is inside the Trichomes because of the PEF?
Yeah, that's actually a really important question to us. And I think now currently we have a person who actually worked on the aroma compound of the herbs that if it's actually changed due to the PEF, and I'm not really think I can say the result. No, yeah, but we found quite interesting result about the aroma compound. Also that it might be preserved. Yeah, it's still there, and in fact that we still make the trichome like intact like that. So I mean, basically, if we don't change any profile of the aroma, I mean the specific substance in there, if we don't change that and the trichome are still intact, I believe that the aroma will still be there.
Okay, that's really interesting, because there's such a GCMS aroma studies would be very nice to have a look into it and to see the profile, because we can have, let's say, keep them together and nothing will happen with them, but at the same time, what is inside is a crap, let's say, so who knows, maybe it's not, but you had a chance. So the smell, the flavor was better. Like when you have finished, let's say, and you have tried, I'm sure that you did. We all do. People that are doing PEF, we all eat food that is PEF treated. So
Yeah, yeah. This is might be a bias, of course, because the only panel here. But yeah, definitely, definitely, I would say that it's worth doing.
Okay, okay, that's good. No, I'm not sure. Sometimes I see that. Yeah, I would like to say that OPEF it works, but it doesn't. So I regret very often, but yeah, it doesn't sometimes work. Like with string onion, for instance, and when I were research it was not good when we have did it. Not good at all, to be honest. I think that I will have one more question, because this method that you have described, I really like that method and I really like the approach. And even though I could accept, let's say, the limitations related to the long term of resting period, yeah, I could imagine how industry could deal with that. Yeah, they need just to have a lot of space, let's say, to do it. But these trichomes that were, let's say, preserved, I find this as the most attractive, let's say, most interesting from quality point of view, from quality perspective, result that you got. But when I think about herbs, is the picture that Aston Federico took, yeah, the first picture of oregano, yeah, they are grinded. So if I will, let's say, keep all the structures intact, and then I will grind them, what will happen?
This is interesting because normally okay, this is a culture thing, but in Asia we don't actually grind.
You have like a leaves, yeah.
Yes, the whole dry leaf, because we know that way is actually better preserved.
So nobody teach European people that. Then we know that we should be teaching.
That's racist to say, but no, but I mean to have dry herb is easier to use.
Yeah.
Right? Yeah, but the problem is that definitely the mechanical process will somehow damage the trichome.
But do you think that this, I mean, like we will still observe the benefits?
Of the PEF, you mean?
Yeah, of the PEF and the technology that,
yeah,
because it's a new technology. This is something new. Yeah,
definitely, because the size of the trichome is still quite small,
okay,
compared to the flakes. I mean, there will be quite a chance that the trichome will be there on the flakes intact. Yeah, but okay. I mean it is still, yeah, mechanical process still degrade the quality, of course.
Okay. Well, I was pleased to have this discussion with you. I know that it's maybe not 1 hour still, but you answered all the questions that I had, and even when I created the new questions, you went through them, let's say, very nicely. So yeah, thank you.
Thank you so much.
Or your microphone?
I don't know.
If you said you have
feel
all
the
your
power.
questions done.
But it doesn't that I want to give it back.
Because I think I need this for the committee as well, don't I? Do you want to? No break. Now we can continue. So then we will continue with the Q&A session. And now it's the time for the committee to be able to ask their questions. And I think we will start with Lilian. So please, here you have the microphone.
Super. See if I put it here. Is it fine? Do you hear me? Yeah. So, Grant, thank you very much. I think I've really enjoyed to read your work. I think it is quite interesting that the way that you approach and when you study the effect of PEF on these cellular structures. And this provides, of course, a lot of understanding of what happens, how PEF affects and consequences for drying afterward. And of course, what is special on your thesis, I also think, is these leaves, because I mean, they differ from other plant cells, or I mean, if you are perforating the whole cell, or you are perforating a leaf, so it's different because you get different structures, right? And that's where exactly the structures that you look at. which I found it super cool. But it's also where I have questions because I haven't seen this before. So now you have to help me to see if I understand or if I understood, because I'm very curious about it. I think it's really interesting. So I start with your first, you start in these guard cells, right? And you have this picture 2, where you do the perforation or the permeabilization of these guard cells. And I mean, and my question is just like, I mean, why is like that? I mean, all the cell is like that. The guard cell are like 2, the stomata, right? As 2 guard cells that make surround this, all, let's say like this. Why, when do you perforate, it looks like this, that you have these 2 parts only? Why not everything is red? I was just curious about, is there an extra structure there that, do you know?
I think that because of the property of iodide, it only stains to the nucleus of the cells. So the bright part that we see, that actually the nucleus.
That's the nucleus of the 2 guard cells. Okay, and therefore you see them like this. Okay, but why? So the consequence then for this inactivation is then the cell opens up, or the guard cells cannot anymore protect the orifice, right?
This question is actually the most important one, but we still trying to find the answer for that. But I mean, we know that when the guard cells open, it requires the water to get inside the guard cells and then like become turgid and then make a pore between them. And I mean, I still don't have the answer. That's why the water goes into the guard cells instead of going out, right? I still don't have that answer, but definitely the PEF actually have an effect on that mechanism, on the controlling of the water transport. Yeah, so that's why it stay open like that. But for the mechanism, I still don't have that.
No, because I found quite interesting this. Then I got a little bit curious, and this follows also these changes in structure. I mean, then you have this figure 4, where you start to follow, which I think is a super nice work. And then after a given point, you see, yes, now I'm perforating these guard cells, right? You see these pairs, right? I think that's how you identify. I think you also explained better in your presentation, because otherwise it was not so easy for me. I was wondering, how do we do this? But of course, you'd look at eye magnification, right? Yeah. But my curiosity was about, I mean, what happens, what do you are perforating before you perforate the guard cells? Because, you know, like some of the pictures, if you look like after, sometime, I don't know, for example, picture B and C, you start to see this, what is that? It's just one of the guard cells, or is other cells? What do we see there?
Okay. I think those are the epidermal cells of the leaf. Yeah, because I found that these, I mean, if we take a look, I mean, I don't have the picture here, but under the microscope, we can see clearly that the nucleus is in the boundary of the cells, like the shape of normal epidermal cells that we can find in the vessel. Yeah, and then in the guard cell, we can see that the guard cell has no electroporated nuclei clearly when we zoom into that.
But do these cells influence also the drying process afterwards?
Yeah, I mean, I think I have the drying curve of the one with the electroporation, but without the guard cells electroporation. I think that is in paper 2. I need to check that. I think the difference is really slightly. Yeah, it's really slightly. So, but I need to think that if I did the statistical
because I mean, I was wondering a little bit, and like, and where is the water in these leaves? Do you know, like, because if you use perforate, you could also imagine that this would have more effect than you see.
I mean,
But yeah, I see your point, but it's interesting, I think. Because I mean, it's a different structure, and I mean, maybe you have, I don't know, other cellular structure, waxes or that protect. I don't know. I think it's interesting. Yeah. So then I have a question also on PEF, and I think you went also on this bipolar, because I also find curious this. I think then it goes on your figure, what is 9 in the paper, blah, 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 paper 2, right? I think was also the figures that you have been there. And I was wondering about this, that you also mentioned better in your presentation, that when the cells die, you can see this very clearly, right?
Yeah.
But in this figure 9b, so you have with the bipolar pulses, right? You need, so with bipolar, you need more pulses than with monopolar for cell death. Is it right?
Yes, exactly. That what I found in the experiment, that the I mean, when we compare the bipolar and monopolar, we can clearly see that bipolar has less effective. So it means, I mean we found less electroporation at the same number of pulse. So it means that the bipolar has less effects to create pores on the cell membrane. That's what I thought. So when it comes to the irreversible level, I think that's why the reversible part is quite far from compared to the monopolar.
Did you expect something else when you start?
I mean we have quite some works from the colleagues that they work with bipolar and monopolar, and yeah, we actually have the same result that monopolar actually working. So the expectation is not so high, but
okay.
But we
No,
think
because
that,
I would expect. So I mean, then of course you have a larger variation, but I was also surprised about that, because it's quite interesting. You also mentioned that, but I was curious about, if you agree with me, if you expect something else, but of course, maybe you have more data than I do. Yeah. So that's nice. So then I have another question about your next structures, your trichomes. I also think it was nice. You also explained better for me than when I read here. So I think it was more clear. I think you'll see better also on your screen, maybe that we see on your pictures. But I want to understand a little bit one thing. I mean, these cells are really like, as you see in the pictures, so they are a little bit, so the leaf makes a little bit like kind of, and then the cells have this three-dimensional structure there. It is like that. Yeah, like a cave. Yeah, exactly.
Yeah, this is actually like one of the limitation actually of the method, because the microscope works by using like high intensity light, and then we can actually see really shallow depth of field, I would say. So that's actually, I think maybe it's a good thing also, because we can scan only like, okay, I will need to draw something. Do we have like a shot or okay, like okay. Oh no.
Now we know it's academia.
Yeah.
Now we are on the board, right?
Oh, you're gonna kill me.
Now we're going.
She's angry. Okay, I need to this one. Okay. I mean, when we take a look at the trichome, it's actually like, so I mean, let's say that this is the leaf, right? Oh, that's the nice one. Okay, and the trichome is here. So what we see usually, like if we take a look at the trichome, it from the top view, it look like only this one and some of the like more like a hole. Yeah. But then if you take a look at the cross section, the leaf will be here, and then it will be like this, just a little bit.
Okay.
and then like a sac of the essential oil. Yeah. So when we take a look from the microscope, we actually need to like look at this plane and then keep scanning it down like with the
Right.
scanning, and then we recompose the image. So that's why when we look, we cannot see this part, right?
I see.
Yeah, we cannot see
Okay.
this
Yeah.
part. Yeah.
So
that's
it
why
is more like round.
Yeah.
So what you see in the figure
Yeah.
A is missing the top
Exactly.
of the structure.
Yeah, that's the limitation of
Now I got it, because I was wondering a little bit how come this structure can all oil. Was a little bit weird by nature. So I was wondering if it was some other things influencing this. And then, I mean, then it comes to this resting that, yeah, has also been discussed, that I also find quite interesting, that this can have an effect. And I mean, and if I understand well, the way that you did resting was you have air sealed the same, so they were in a moisture paper for 24 hours, so they have enough water. It's just water, it's no other nutrients.
No.
No. And then it's in the dark at 20 degrees. What happens there?
Yeah. No.
Yeah. What do you think happens? I mean, and which structures are really affected by this? That affects, is the stomata that are affected, or is this trichomes, or
Yeah.
what structures will be?
Ooh. Yeah, that's what we really want to know.
What do you
actually.
think?
Yeah. And yeah, I mean during the resting process, there's a lot of things that could happen. Like because the thing is that we, first of all, we need to expect that we stress the tissue and the cells in the electroporation process. So we expect them to fight back, of course, because we create pores on their cell membrane, and when they reseal it, I mean how to say that, I'm not really sure like what really happened there, but one thing that I think they need to do is that they need to try to regain the chemical balance that they have when they used to be natural. And with that, I actually take a look at the heat that they produce, and I found that it's like 3 times bigger.
Yeah.
So definitely they quite struggle. I would say they quite struggle to get back to their natural
So it's like
state.
natural physiological mechanisms to try to repair the damage.
Exactly.
That's what you think, and
Yeah.
and
So
that way they get.
Yeah, so I think they might produce some metabolites that actually have like a side effect to protect them from during the drying process, but that we don't know. That's my guess. Yeah.
So if you had like nutrients there, would that go faster?
That could be. That could be. I think.
Or
Wait.
not? Maybe not. Maybe
Yeah,
they
maybe,
will just die from too much food.
Yeah, but we need to have the way to give them nutrients during the raising process, which we have
because
some,
on the other side is in the dark. That's also what I was wondering, because then I was okay, then it should be light, then it's in dark. I mean, but yeah, I don't know what happens during when it's dark. The plants, I guess they don't sleep completely. So then I think it's interesting. It's nice. Yeah. Something to investigate further is good. That's not done everything. I mean, then of course this influences this drying, the next drying steps, and maybe you are going to get a lot of questions on drying, so I can also say, but I was also curious about this. I mean, why vacuum could cause more damage and then air drying?
Yeah. I mean, to be honest, this is not what we expected.
No.
Yeah, because ambient temperature, come on, it's need to like have less damage. But after some discussion with Inyat also and Federico, and this, I mean, one thing that I didn't control during the vacuum drying is that I just decreased the pressure quite fast. I would say that like the maximum capacity of the machine, and then it, after that, it will stay in the vacuum state for like some time, and then I release it immediately. So that might damage the cells. Yeah, that part.
Because that's in fact what was going my question to you, that if exactly the vacuum conditions that you have used have been more the reason, like this fast removal of the vacuum, or the other way around, that could be caused more than just vacuum by in other conditions it could eventually. But of course it's you have to check other condition. But could be good to be maybe careful in this conclusion, because maybe it's not always valid. Then I mean, I think I just have also a question. I think it was nice, your presentation became also most things clear. I think it was good that you put a picture how they look like. Usually, I mean, I think we can buy some that are better than these ones that they have there, but still, how do your look like? Do you know, if you would have put pictures of your own basilica leaves, do you know, then you have like, these ones that are beautiful, and then you have these ones that you buy, they are pretty bad. And then how do they look your own?
I mean, unfortunately, I didn't put some pictures.
You could?
But it looks okay. From I mean, it's definitely better color. You can see that, with your eyes.
So they are green, I guess.
Yeah, they are green, and then they are. This is no measurement, but they are less shrink.
Yeah,
that's what we can see. Yeah, and aroma by Ashley. It's good.
That's what you are also evaluating for the. Good. Yeah, thank you.
Thank you so much.
That's what I had.
Thank you, William.
Oh, of course.
Sorry.
It's not easy. So I will go to now the industrial side of this maybe, and ask Dr. Gerald to ask some of his questions.
Thank you. Thank you for the wonderful presentations, and reading the work was really interesting. I think before going into a real industrial question, of course, this whole scheme, this whole project, of course, is about manipulating nature. Since, of course, the nature is all about here control over transport. Limiting transport or inhibiting transport, or even selective transport, and you try to manipulate that by this technology, even in a way that you say, okay, we try even to make it keep it viable in the process, and then killing it afterwards by fully drying it. And you of course illustrate the effects of the different reversible and irreversible electroporation and the guard cell effects. And when I looked at the drying rate in paper 1, I first thought, okay, that's interesting. But what I missed there was the temperature where it was dried at. I could not find it in that paper, by the way, but maybe I overlooked. But looking into the graphs, which give, of course, a nice view. First thing I thought, okay, why didn't he plot them also in a log scale? And second, I thought, okay, then you attribute, of course, the effects of the opening or keeping open the guard cells, for instance, on the increase or the decrease of the drying rate. But then I think, okay, so then you have basically two. Or maybe more than two ways of how the transport will go. So through the electroporated cells in general, and also the guard cells. So I think, okay, can we also make it more quantitative? So I wondered whether you had an attempt in doing that. See, okay, you have the effects, you calculated the diffusivity, and you have actually now more ways at which the flow can go. What is then, how much of the flow will go through the guard cells, and what kind of flux can you did you do any calculations on that?
Oh, definitely, I did do calculations on the capability of the guard cells to release the moisture. But after I did the literature, I mean the major way of the leaf to release the moisture will be the guard cells. Like more than 95% of the moisture will go through the guard cells, because the leaf has like a cuticle layer that block the moisture. So definitely the major pathway of the moisture to get out is through the guard cells. So I mean in the control sample, let's say, the guard cells, some of the guard cells will be open, some of them will be closed, but in the PEF, we expected that most of the guard cells should be open. So I mean, the obstacle here is that only the closed guard cell that will block the moisture. So that's only difference. And also I calculate the diffusivity of the sample. I think that is in paper 2, but that is like many years ago. I need to check that again. To check that. I remember that I also did that. Yeah, table 3. Yeah, I actually calculate and then compare, and then the effects of the guard cells electroporation is shown in the diffusivity also. Yeah.
Yes, but not that you say, okay, I can attribute so much in the water loss to the guard cells and the rest to the other electroporated cells. That's of course more difficult. It becomes a bit more okay. In that respect, I also wondered, did you observe during the drying any drip loss?
Any
drip loss?
Oh, the drying, during the drying process.
Yes. Yes, after
you mean after the electroporation and
during drying, that I can imagine if the structures are more open, that there is also actually options for water, liquid water to
leak out. No. I mean it's hard to say actually, because what I did is that and in the drying system here is the closed system that I didn't take a look at different time like that on the sample, but that's interesting. I mean think about that. Okay, let me think about that a little bit. We open the stomata and the water. I mean what I imagine is that the most of the time, not most of the time, the major way that the leaf lose its moisture is through to the cell membrane first, and then it goes to the cell wall, intercellular space, and then goes into the spongy mesophyll, the surface of it, and then evaporate from that as a vapor from the guard cells. So I think if this is the case, I think if we put the leaf there, most of the time the water will be vapor already in the spongy mesophyll. So it shouldn't be in the liquid form.
But then the effect of vacuum drying would maybe also be, or is that then still logical, that the vacuum drying still has a negative effect on the overall quality?
Yeah, the vacuum dry is still, but that I think that mainly because of the releasing of the pressure. I mean, if we can control that, it might give a better result. Yeah, control the rate of the pressure rise and depressurizing.
Yeah. Okay. Yeah, indeed. There's already quite some questions about the resting time. And I first thought the resting time, what is this? It sounds a bit like giving a convicted criminal a very lengthy final meal. And I think you, well, of course, the sweet spot would be that you can indeed reduce the time or make it much shorter, because I've been standing next to quite a huge dryer, industrial herbs dryer, several times. Yeah, that is really, there comes a big lorry comes in and it puts the thing. There is not so much washing or things with water or anything, cutting and directly on the belt. And when, with actually much higher temperatures, it goes off in much shorter time. So then introducing a resting period. Of course, the PEF is already, I think, scaling up is still a bit of a challenge to some extent still, but the resting period, indeed, I agree, it can lead to all kinds of scalding, brewing, microbial problems. That's for that part. I would quick question about paper 3, and you basically use that survival as a measure, an artificial measure for the food quality, which I found interesting, because, well, in the end, of course, you're not interested in the survival, but in the actual food quality. But do you think you can use that that's better to choose the conditions that you say, okay, in the end, this will lead up to better food quality in the end? Or did you do any things with turgor structure measurements?
Yeah, one thing that I found, if we do the irreversible electroporation, the quality will be degraded right away, Even, I mean, if we want to apply this into the industrial, and one thing that we don't want to see is to, have one process and then the leaf just discolor, the leaf just lost the aroma already. So that's not what we want, but somehow in the end we still want to have that increased efficiency of the PEF, right? So I think the reversible electroporation is the only way to cope with that. Yeah, because we don't see any quality degradation right after the process.
Okay. Yeah, and of course, also related already in paper 4, you compare the normal ambient pressure compared to the air drying and the vacuum drying. And in paper 1, you looked at all kinds of different drying techniques. So what I was thinking, okay, if we couple the experience from both, do you see certain advantages or disadvantages also for other drying techniques in combination with that?
Okay. What we know so far right now is that PEF resin could be used to protect the tissue from heat. That's what we know. And also the convective drying like that. So I think that this technique will probably work on the drying method that rely on the same mechanism, like sun drying. It should work. The shade drying also should work, like the heat pump, basically the convective drying also. Yeah, it should work. And the one that we are not really sure is the one without the utilize of external heat, like the freeze drying. And I'm not really sure about the microwave drying. It should work, right? It should work. Yeah. Yes. So let's say that I think most of the drying method should work with PEF. Yeah, most, but not all, definitely.
Okay. yeah, of course, you also reflect on using other in your future outlook on other vegetables or other than only the Thai one.
Oh.
That was you choose that because it was sponsored by
Not
Thai
really.
government, or
I mean, this is what really happened. We used to work with Italian basil first, and then we had a problem with the material, and then we in the end we go to the grower, and then like try to find the herbs because we know that the herbs that has the stomata actually work with this method. So what we want is the herb stomata, which all of them had it. So in all of the options, I just found that, okay, this is also Thai. So that is a little bit of the impact there. Okay, this is Thai, so I'm Thai. So yeah, let's work with that. It's just a little bit of impact.
so it's a good bias to start with that turned out to be very
Yeah.
very good. Okay. Then I think I had most. Well, the only thing what I has more as a comment than that's on that future outlook. I found that that your work was more would deserve a longer chapter there. Since I think you've done a lot of interesting things, and I think yeah, especially if you come from industry, you want to know a bit about, okay, what does this work, how does it bring further, or how far are we now from implementation? Maybe that's a bit too broad a question, but still, how does it attribute to the steps towards it? And I think there's plenty of steps to be mentioned. So I still give you the floor if you say, okay, I have something to add there.
Yeah, I mean, we know that it's actually working. We know the type of material that could work. We know the drying techniques that could work with this, and we know that there will be a market for better dry herbs for sure. And still, we're still quite a long way, I would say, because at least if let's say that the manufacturer produce like 5 types of herbs, they need to find the 5 protocols to work with. So that's a challenge, of course, and the standardized problem, because yeah, I always think about the standardization in industry, because they really need that to make everything work smoothly. So this one will be a challenge that we need to work with, that every batch of the herbs that comes, we need to be able to electroporate into that gap that we have for each type of herbs, and then yeah, there's still a lot of work to do.
Because did you see a lot of seasonal effects in the
yeah, the seasonal effects, I think I did that in a separate experiment also. I don't really remember, but in the end, it doesn't really affect the drying curve. So that was what we checked. And but as you know, that I didn't go to the deep of the mechanism of biochemistry there. So I'm not really sure. Like in different season, it might have different effects.
Yeah,
but
of course,
probably.
Yeah. Also on the conditions that you would use.
Yeah.
Perhaps.
Yeah.
Okay. Well, thank you.
Thank you so much.
So thank you. And now we go to the last but not least member of the committee, and that's Leif Bülow. So.
Okay, thank you so much. First of all, I would like to congratulate both of you. I mean, you made excellent summaries, and it was really a pleasure listening to both of you during this discussion.
Thank you.
We learned today that 1987, that was a magic year. So my question to you, when was your magic year? When did you start here in Lund?
Oh, that was 5 years ago, actually, like 2017.
2017 was your year. So
But it's not so magical, is it?
no, maybe not. But at that time, you made a study plan, an individual study plan. And now we have, let's say, seen your thesis. And my question to you, did you follow the plan? Or how was the original plan?
I think everyone here in this room can answer that. Yeah, it's changed quite something. Yeah.
Yeah. How did it change? It could be interesting to hear.
Yeah, I mean, the first goal was to, at least in my mind, was to get a Nobel Prize. We expect that. I mean, let's think about that. But this is all imagination right now because we prove that it's not happened. We tried, the ultimate goal here is that we can produce dry herbs that can restore fully after the drying process. So you can have the dry basil leaf that can come back to life after the rehydration. And that is the ultimate goal. But as we know that it's not that easy. So we changed our goal just to the reality. Yeah, and what we actually have in the thesis. And then, yeah, we changed quite something. Like we were planning to work with other drying techniques also, and then also other pretreatments like vacuum impregnation, that we can add the nutrients to the leaf and then have it like better resting. But then a lot of things happen, and then we didn't get that, and then we need to change our goal. And yeah, here we come. Yeah.
Okay. Well, I mean, I think it's a good track record, definitely.
Yeah.
But if you think about it from a consumer viewpoint, I mean, what's important for the final product? I mean, you look very much on to say, the looks. I mean, it must look green.
Yeah.
But from my viewpoint, when I look upon herbs, I think the taste is important.
Definitely.
But
Definitely.
you indicate here that, I mean, you would like to taste the aroma. But I mean, how should one do when you look upon the aroma? What's needed?
You mean the aroma of dry herbs, like
Yes,
because
yes.
Yeah. I mean, what we know so far is that the main contribution to the aroma is the essential oil.
Yes.
So that is like what we expect. But of course, the consumer won't really know that. Okay, we need to have the oil, but we want to have the treatment that can at least try to preserve the trichome first, make it intact, because we know that the essential oil is there. And then after that, after my colleagues' work, we will prove that the aroma is still also intact in profile. Yeah.
But if you look upon a plan, when is the proper time of tasting? Because I mean, now you say that, I mean, you want to move on with GCMS, for instance, but I would like people to taste, because I say tasting should become and started before you do the GCMS. How do you reason?
Sensory analysis.
Yeah, sensory analysis. When should that come into your plan?
Actually, it's in the future outlook right now, because I mean, we actually plan to do that, but unfortunately we don't have enough time to taste the basil, but it actually needs to be done
but I guess you have tasted it yourself.
Yes, of course.
Yeah, I realize that.
Yeah, but biasly is okay, but normally I mean, this is personal culture, because we don't actually use Thai basil in dry form.
No.
Yeah, but I mean, when I like try to smell compared to control and the beverage, I just smell it.
Yeah,
it is actually have stronger taste. Yeah.
Both of you discuss, I mean, this with reversible or irreversible electroporation. But what in principle, the definition is simple.
Yeah.
But in the real world, it's much more complicated. So where are the borders for being reversible or reversible? Because I mean, you have a population of cells. So what do you mean when you say reversible?
I think that is down to the end of the electroporation. If the cell is still can continue its metabolic activity afterward, like if the tissue still can, I mean, for example, like in the FDA test, before I did the FDA test, I need to wait for like 20 hours to make sure that it can come back to life or just die, because during that it will decide where to go, if you want to go to heaven. Or,
no, but I'm thinking about the population of cell, because I mean, do you think it concerns all cells, or is it acceptable if you, let's say, kill 10% of your cells or half of your cells or 90% of your cells? I mean, that's what I didn't actually do the quantitative, but I'm not really sure if there's a limit to that. I think it's different in different type of material also, and like how many percentage that the cell is still alive, that it can continue the mechanisms that they have. I think it's something that you can define yourself, actually. Another little bit more technical point is that I noticed that during your electroporation, you were always using 50 millimolar sodium chloride. Did you discuss other solutions? I mean, let's say higher or lower concentrations of sodium chloride?
The key here is to try to control the conductivity of the solution, so that we can make sure that the pulse is actually delivered in the same strength to the tissue. And I think the idea here is that, let me think why we use that 130. I think it's actually referred to the previous work that they also choose this one, and like it's almost like a standard protocol that we have in our lab, that we're gonna control the conductivity to be this level for every treatment that we have, so we can compare the effects. In that way.
Because I think you can control quite a lot by having differences there as well. We discussed about your individual study plan, but what's the future plan for you? What happens next?
The future will happen, but I still have plan to work in academic. Of course, I have a contract in the university in Thailand, and also like a YouTuber. Now I'm a YouTuber. Hey, no, the camera is there. We're actually live on YouTube right now. And I want to pursue like this technology, because I still think that there's a lot of room for improvement for this technology, and also, like, if you think about plant leaf material, they all have stomata, and it means that if we can make something benefits to the opening of the stomata, every plant should have benefit from this treatment. So I would like to pursue this thing. And in fact, in Thailand, we don't actually have the machine. So it would be interesting to set up a lab and then start working with this in Thailand.
Okay, very good. Thank you so much.
Thank you.
So now the committee has had the time to ask questions, and then we generally let the floor ask questions, but I would actually want to first ask the deputy members as a part of the floor if that you have questions to Grant.
Yes, I have actually.
Yes, I thought so.
So in paper 2, you describe the moderate electric field treatment, where you used AC currents and considerably lower electric field strengths than you have at pulsed electric fields. So my question is, how do you know that you have selected a process window, which actually gives comparable conditions when you look into that.
Let me think. I think the answer will go to the energy that I'm not really sure. Let me check. I'm not really sure if I actually calculate the energy, but think about this a little bit, because that was a long time ago. And yeah, I think at that time we tried to electroporate the cells with the MEF, moderate electric field, and then what I saw there is that is not really effective to electroporate, and it's quite struggle even to electroporate the epidermal cells, which but I mean, so I didn't go that far to try to work with MEF to the guard cells, because it is like, I think it's beyond our range, and then in some point MEF is a continuous process. So if you pass through the current to the solution, it will generate heat, and at some point it will start bubbling up, and the electrode will be corroded. And that's not what we want, and it's gonna ruin the result. So that is the limit that we need to stop. So in that range, we cannot find the gas cells electroporation. So we need to just call it out. Okay, this is not working. Yeah.
Okay, thank you.
Do you have questions, Andreas? So we have from the other deputy member of the committee.
Thank you. Yes, I agree. It's been very interesting to listen to your both the presentation and all the interesting scientific discussion we've had here. I was curious about one thing when I read your thesis. So I think let's take the opportunity to ask a question. We have already got a lot of interesting questions. That's about the drying kinetics.
Oh, okay.
And I understood from before here that could be almost a religious question, so I should be careful a bit maybe. But if you look at the drying curve, you have really looked at those a lot. What would you say about the drying periods here? Can you see a clear demarcation? Can you see a constant rate and a falling rate period, or several falling rate periods or so?
Yeah. I mean, in the drying curve that I got from paper 2, definitely the constant rate period of the gas cell electroporated sample is like it reached much lower moisture ratio. It just goes straight down like that. And I mean if we take a look at the falling rate period, right, the slow part, we see that PEF actually like makes the sample to go to that faster, in faster time. So the constant rate period occur like quite faster in comparison to the control. Yeah.
So most of the things here seems to occur during the falling rate period. The constant rate is just a very short
really short.
That it goes through. Yeah. And also I was very happy to see that my heart always feels a bit warm when I see equations. And you did some kinetics fitting also to kind of describe the kinetics, as I understand it, of the drying process. You used 2 different models for doing that, right? Both page model.
Yeah, I think I used page model. Yeah.
Yeah, and the effective diffusivity. So my first question, I mean, quite technical, but I was curious. In page model, what is n here in your case? Did you set it to 1, or did you evaluate it using parameter fitting?
I actually used the let me think about that, because it's really long time ago, and I did that only one time. And what I did there is to use the program to calculate the optimal n parameter. For the page model. So I don't know how it calls, but what is it called? So I put the page. Yeah, fitting. Yeah, okay, fitting. Yeah. So I just put the model and then have the estimated n.
Nice. Because I think I couldn't find the value of n. Sorry, it is. Yeah. It was the unit of k that confused me a bit, maybe, of course. Yeah, I see. We have the n there. My question was also why when you decided to make this kind of kinetics fitting there also, what were you thinking going into that? What was the reason you wanted to add a kinetic fitting part?
Yeah, the one thing that I want to see is that we need to have some kind of parameters to compare between treatments. So definitely the diffusivity will tell us about that. So that is the goal, to have the kinetics. And actually, as I remember, I think I did quite some numbers of different models, and yeah, I come up that the page model is actually the fitted one. So yeah.
So it's the page model was the one that fitted best, and then the other one, because you can always just measure the drying time. That will also be a measure of the difference in.
Yeah, that also working, but then we're not gonna see how the PEF actually affects different stage of drying. So yeah, so the curve, I mean, I think it will be better to see like if it's like go fast and then slow, or it's just another type of kinetics. So that we can compare the different two drying curves right away. Yeah.
So for the effective moisture diffusivity model, you only looked at the decreasing, the falling rate period to get a measure of that specifically. That's the idea then. You only use the data from the falling period to calculate the effective diffusivity.
Yeah, exactly.
Yeah. Then I understand. So you get a separate quantification of that phase. Then I get it. Yeah. Also, when we talk about this kind of kinetics, talking about an effective diffusivity and talking about the mass transfer rate to from the boundary layer at the surface, things like that. And the way I usually think about it, because I don't know anything about plants and cells and things like that, I just think about it as we have kind of an interior which is homogeneous and described by an effective diffusivity, and then we have a boundary layer which is described by a mass transfer coefficient. But now with all your knowledge and your nice microscope pictures and things like that, you see that it's not as easy as that.
No,
it's something very different. It's not two different parts. It's not one uniform interior and just the boundary layer up there. Yeah, what are your thoughts? I mean, because this kind of modeling you do here with an effective diffusivity kind of assumes that we have a much more simplified. Can we still say something from the effective diffusivity?
I think definitely like different models should be tested at least, and also not only the mass transfer and also the heat transfer, because after the PEF we still have not enough information to justify that the heat transfer will be the same as the control and treated one also. And I actually try to read some of the papers that talk about this, but there's quite a few of them. Yeah, and I think one is your paper. Yeah, last year. Yeah, yeah, the Louis-Koff model. Yeah. I read through that, and it's also like different in leaf and apple tissue. Right. Yeah. And it is quite different because apple tissue we have like a large parenchyma cells, a lot of them, and here in the leaf we have cuticle, we have epidermal, we have mesophyll, we have spongy mesophyll, and we have gut cells. So the model will be, I mean, if one could develop like a specific model for that need to be really goes into the depth of that to come up with a suitable model. Yeah, and it would be interesting to have that also.
So if I understand it correctly, what they do in these models then is that they kind of try to build multiple levels, which is more related to the plant physiology.
Yeah.
That's
So that would be super interesting.
More future works maybe.
Oh, there's a lot more future works.
But thank you very much.
Thank you so much.
And now I open up for questions from the rest of the audience. Yes. Lingpi. Yes.
You want to have a power.
Looking at that. Very great presentation. I think I learned a lot by how the way you design your slides and how do you present them and how to connect the things. But here I'm really interested about how this procedure going. So at first, when I see the slides from the opponent, I thought you have electric field here, and then you have your plant here, and then finished. And then I see the machine, and I thought it's okay, you pick up the leaves and you put them in the machine, and then they finished. And then I thought that you have your leaves in the water, in the machine, and then goes the electric. I wonder which way it's actually do in reality.
Okay. Let me draw it for you actually, because this is a shame, but I didn't take a picture of the setup. I mean, everyone should do that, right? When you have an experiment, you take a picture of the setup, but I don't have that. So let's say that we have, we have another one. I want to do this for a long time because I saw lecturer doing this and this looks cool. Okay, so let's say that we have like a generator, the both electrode here. So what I have in the lab actually is actually like a chamber, it's basically a box like this made out of acrylic, so you can see through it, right? And on the top of this is one electrode, right? And in the bottom, that's a nice drawing. No, not so nice anymore. Mess up. And and in the bottom of this, you have another electrode connected to this, and this is like the lid that you can remove. So you put in the sodium chloride solution here, and then you put the leaf in, and then you close the electrode. So here there will be only electrode and leaf here and cover with the solution, and then you pass through the electric field. So this plate actually made it to the electric field, so it go like that, and then it passed through the whole leaf, at the same time. So that is actually the
very clear now. Thank you. Because then I have an assumption based on the question about how to control the micro biological hazard. Because I was thinking, what if we can just use UV light to shine on the water without anything else? Then you kill the bacteria in the water. Then maybe less hazard with the microbiological issues.
Actually interesting. Only one concern, no, two. We need to make sure that because UV light cannot really penetrate all the sample like that, so it mainly kills the surface of it, right? Kill the microorganism on the surface. So the leaf has two sides, so we need to somehow, that one. And another one is the aroma, because I know that UV can actually activate some oxidation of this essential oil, so that might degrade the aroma. And also we have like a UV light pulse. That actually like apply the UV light impulse, just like the electric one, and but instead with light, and that also makes the electroporation, not poration. It's not electro.
There are some physical effects, but it's rather different mechanism.
Yeah.
But it will kill for sure. But oxidize as well.
Yeah. Thank you so much.
Okay, I think I saw one more question from the audience. Yes, Peter.
I agree with the previous speakers. It was a very good presentation. I'm wondering about the resting period that you've chosen. Now, if you look at the calorimetric activity, something is happening up to 1 hour. Then after 6 hours, something is happening again. And then nothing happens. So why choose 24?
The idea, the first, I think the first idea is to, because we actually didn't know before that it would take 6 hours or less than that. So we chose the time that will allow the cells to, I mean, try to give the chance that it will be something happen. And of course, we can see the difference in the thermal power and the heat produced that actually shifting like that. But we actually still don't know that what about the things that happen without the change of the heat. There might be something like that we still don't know. So that's why we chose the 24 hours. So I mean I think I also did the 48 hours and even more, but then we have the problem with the bacteria. So it start growing and then it spoil the vessel. So we choose the maximum time that we can control the microorganism. Yeah.
Thank you.
Then I will look at the audience once again so that I don't miss any questions. And if there is no question, then this part of the session is over. Yes. And now starts the serious and the fun part. So the serious part will stay here, and the committee will have a meeting here. The fun part will go to Cafe Esther, and the committee will join you when they have made a decision. So please, everyone, I want you to, as quick as possible, you can stay for the serious part.
Unfortunately.
So supervisors and committee will stay for the serious part. And then I can, and then we
turn this off, right?